The 200,000-mile Liu. Go out to your driveway on a cold morning, turn the key, and hear that deep, hollow metallic knock coming from deep inside the engine block. You end up at a local dealership service bay, staring at a printed estimate that matches the down payment on a small piece of land. The service writer tells you, with a sympathetic shrug, that 200,000 miles is simply the natural limit of a modern vehicle. The metal wears down, the clearances widen, and the machine dies. You accept it because everyone else accepts it. You pay for the replacement, or you sign papers for a new loan, participating in a cycle designed to keep you financially dependent. Now, contrast that with a very different scene. Drive down a quiet gravel road just outside Millersburg, Ohio, into a small workshop heated by an old cast-iron wood stove. Inside, there is a stationary generator engine that has been running on the same factory engine block since 1961. That is 64 years of continuous service. No teardowns, no line boring. It still uses the same original pistons, the same rings, and the same crankshaft, rotating in its original journals. The man who operates it spends exactly $1 every 4 months to maintain that state of preservation stop. And think about that for a second. $1. 64 years of mechanical life from an engine that modern engineering tells you should have been scrap metal decades ago. The witness in Millersburg, when I first walked into that workshop 3 years ago, I assumed it was an illusion. The scent of dry sawdust, old gear oil, and cold iron hung heavy in the air. I leaned down and pressed my bare palm against the cast iron block, expecting to feel the harsh, staggered rattle of a tired motor holding on by a thread. What I felt instead was a deep, rhythmic hum, a fluid smoothness that completely contradicted the date stamped into the metal casting. Marlon, the Amish farmer standing next to me, didn't offer a complicated lecture. He simply pointed to a small glass jar sitting on a wooden shelf above his workbench and said, "The old companies buried this formula back in the 30s. We just never stopped using it. Understand this. I am not a scientist with academic credentials, and I am not here to sell you a miracle product in a colorful plastic bottle. I am a practitioner. I speak from the position of someone who used to change his oil every 3,000 miles, used only the premium brands recommended by the manual, and still watched two perfectly good engines die before reaching 250,000 miles. I did everything the modern maintenance system told me to do, and I still lost the tools I depended on. What I discovered in that workshop changed how I look at every machine I will ever own. But before we go any further, we must establish an honest limit. This method is not magic, and it is important not to exaggerate what old knowledge can do. It will not weld a cracked cylinder head back together. It will not replace metal that has already been thrown through the side of an oil pan. It will not fix a shattered timing chain or a spun bearing. If a machine is already a catastrophic mechanical wreck, this cannot save it. This is a preventative shield, not a resurrection tool. It works where the metal surfaces are still whole, protecting them before the wear becomes terminal. The science of boundary wear. Why have you been taught that engines must inevitably wear out? Ask yourself that question. If a piece of iron is constantly separated from another piece of iron by a film of oil, how does it degrade? The truth is that engine wear is caused by a specific physical breakdown that happens every single time you turn the ignition key. Standard motor oil is designed to flow and reduce friction under normal parameters. But inside the combustion chamber, at the top dead center, where the piston ring stops for a microsecond before changing direction, the pressure and heat spike beyond the oil's capacity to maintain its liquid film. The oil squeezes out completely. For a fraction of a second, it is raw metal scraping against raw metal. This is called boundary lubrication failure, and that is where your engine dies. One micro scratch at a time, over millions of cycles, Marlon reached up and took down that small glass jar. Inside was a simple white powder, soft as talc between the fingers, completely odorless. It wasn't a rare compound mixed in darkness. It was sodium tetraborate, known commonly on the commercial market as borax. The exact same box your grandmother used to scrub grease off the kitchen floor. It sounds impossible until you look at the historical records and the verified science that the lubricant industry quietly pushed to the margins. In 1933, an independent chemist named Alan Ray Putnam filed United States Patent Number 1987904. He discovered that when specific boron compounds are introduced into an internal combustion engine's oil supply, under intense heat and pressure, they don't just float in the lubricant. They change state at a molecular level. The Soviet Academy of Sciences confirmed this exact mechanism in 1964 during Cold War research on heavy tank engines. When the boron molecules hit the extreme heat of the cylinder wall during combustion, they form what tribologists call a tribofilm, the gravel road analogy. Imagine your cylinder wall under a microscope is like a rough gravel road. Standard Oil acts like water poured over the gravel. It helps things glide temporarily, but the stones still grind against each other under a heavy load. The borax compound acts like a layer of molten glass poured over that road. It flows into the low spots, bonds to the iron molecules, and creates a perfectly smooth, glassy armor that is harder than the metal itself. Even better, this tribofilm is self-healing. Every time the friction of the piston ring tries to scrape a micron of it away, the extreme heat causes more boron floating in the oil to instantly migrate to that exact spot and rebuild the layer. The metal underneath never actually touches the piston ring again. The Forgotten Records in 1983, Dr. Marcus Wenzel at the Southwest Research Institute ran accelerated wear tests on heavy-duty diesel engines using these exact compounds. His findings, later published in a small journal called Lubrication Engineering, showed that the wear rate dropped to less than 1/10 of what standard lubricants achieved. Yet, the research was shelved. The small companies producing it were absorbed, and the market shifted entirely toward temporary chemical additives that guarantee you will eventually return to the parts counter. But the traditional communities in Ohio and Pennsylvania never read the corporate trade journals. They kept mixing it themselves, passing the knowledge down at kitchen tables. Marlon showed me a cylinder liner from an old 1947 Wisconsin engine he had disassembled after nearly 4 decades of constant farm use. The original crosshatch patterns cut by the factory honing stones were still as sharp and defined as the day the engine left the assembly line. There is a second element to this system. A pure carbon suspension the older practitioners call black, water, which fills the microscopic pores of the metal before the borax locks it into place. When you combine the white powder, the black water, and a specific mineral carrier derived from limestone bedrock, you create an environment where mechanical wear virtually ceases to exist. You do not need a specialized machine shop, and you do not need to spend more than $15 at a local grocery store to prepare this treatment in your own driveway this coming Saturday. It requires no complex tools, just 10 minutes of your time, but understand this: precision is everything. The difference between a protective shield and a ruined oil pump comes down to the exact ratios, the critical temperature threshold where the carrier oil must be held during the mixing phase, and the precise sequence of introduction. If you miss one step, you are simply dumping raw laundry powder into an expensive machine. Let me step over to my workbench, pick up the scales, and show you exactly how the old practitioners prepare this mixture, how the chemistry behaves when heated, and the exact steps required to introduce it to your vehicle safely. Setting the bench step over to the workbench with me. Before we touch a single ingredient, wipe the surface down until it is completely bare. In the world of traditional mechanics, contamination is your first and most persistent enemy. A single stray grain of shop dust, a flake of rust from an old wrench, or a drop of residual solvent can ruin the suspension we are about to create. Look at what we have laid out here. It looks less like a modern garage assembly and more like an old apothecary station, a clean, 16-ounce glass mason jar, a dedicated stainless steel saucepan, one you will keep in your shop and never return to the kitchen, a reliable dial thermometer that reads accurately between 100 and 200 degrees Fahrenheit. You're measuring spoons and the three raw elements, the white borax powder, the fine black graphite, and the bottle of mineral-rich spring water. Take a moment to observe the materials. The borax should be completely dry, a pure, stark white powder that feels soft and slightly chalky between your fingertips. The powdered graphite is different. It is a deep, light-absorbing gray, so fine that it behaves almost like a liquid when you tilt the container, slipping smoothly against itself with a distinct metallic sheen. Understand this before we begin. Rushing through these steps is exactly how a good concept turns into a mechanical failure. The old practitioners in Holmes County didn't look at their watches when they worked. They looked at the materials. They let the process dictate the time. Step 1. The thermal dissolution. We begin with the water. Pour exactly 12 ounces of your high-calcium spring water into the stainless saucepan. Place it over your heat source. A small single-burner camp stove or a hot plate works best out in the shop. Set the flame low. We are not trying to boil this water. Boiling will cause rapid evaporation, altering our liquid volume and throwing off the entire concentration. Slide your thermometer into the water and watch the needle rise. We are looking for exactly 140 degrees Fahrenheit. As the water warms, you will notice a faint, earthy scent rise from the pan. That is the mineral content, the calcium and magnesium, reacting to the heat. Once the needle touches 140, hold the temperature steady. Now, measure out exactly 1.5 tablespoons of the dry borax powder. Do not dump it in all at once. If you do, it will clump at the bottom of the pan, forming a hardened, crusty shell that insulates itself from the liquid. Instead, sprinkle it in slowly, a quarter spoon at a time, stirring constantly with a clean stainless spoon. Watch the transformation. The water will instantly turn a milky, semi-opaque white. As you continue to stir with a slow, rhythmic motion, you will hear the faint, gritty scraping of the undissolved crystals against the bottom of the pan. Keep stirring. Within about 2 minutes, that scraping sound will fade into complete silence. The milky cloudiness will begin to break, clearing up until the liquid becomes translucent again. The heat has forced the water molecules to open up, locking the sodium tetraborate into a tight thermal solution. Step 2. Suspending the carbon with the borax completely dissolved and the liquid clear, turn off the heat source. Do not let the mixture cool down just yet. While the solution is still holding that 140-degree residual heat, take your powdered graphite. Forge out exactly 1 level teaspoon of the graphite. Gently tap the spoon over the saucepan. The moment that gray powder hits the water, it will spread across the surface like ink on paper. It looks almost alive, swirling in dark, oily currents before sinking into the depth of the fluid. Take your spoon and begin stirring again, using the same slow, circular motion for a full 3 minutes. Observe the consistency change. The liquid will turn completely black, a deep, dark obsidian color that allows absolutely no light to pass through it. It should look like high-grade fountain pen ink or liquid velvet. The graphite particles, being microfine, are now suspended within the borax solution. The borax acts as a natural bridge, keeping those tiny carbon structures from clumping together and settling out of the fluid. Pour the warm, black mixture out of the saucepan and into your glass mason jar. Hold the jar up to the light. The sides should be coated in a smooth, uniform gray film that drains down slowly, leaving no visible clumps, no dry flecks of powder, and no sediment at the bottom. Let the jar sit on the bench until it cools down to room temperature. It is now ready for the machine. Step 3. The engine infusion. Take the jar out to your vehicle. The engine must already be at its full operating temperature. If the vehicle has been sitting cold, start it up and drive it for 10 or 15 minutes until the oil temperature is stable and the metal inside the block has expanded to its natural running clearances. Park on a completely level surface. Pop the hood and leave the engine running at a clean, steady idle. Listen to the motor for a moment. Take note of the sharp clatter of the valve train and the small vibrations humming through the front bumper. This is the baseline, the sound of raw metal relying entirely on conventional boundary films. Pick up your mason jar. Give it a vigorous shake for about 10 seconds just to ensure the suspension is perfectly uniform after cooling. Carefully unscrew the oil filler cap on top of the valve cover. You will feel a warm rush of air and the faint smell of hot, used motor oil. Slowly, with a steady hand, pour the entire 12 ounces of the black mixture directly into the oil fill port. Dewarm the cap immediately and twist it until it locks. Now, look at your watch. Let the engine sit right there at idle for exactly 15 minutes. Do not touch the throttle. Do not rev the engine to help it circulate. At idle, the oil pump moves the fluid at a predictable low shear velocity, allowing the borax and graphite mixture to distribute evenly throughout the entire oil galleries without being torn apart by high-velocity mechanical stress. Shut the engine down. Now, walk away. Leave the vehicle parked right where it is for at least 4 hours. Stop and think about why this rest period is non-negotiable. The heat of the idle period has carried the solution to every cylinder wall and bearing surface. As the engine slowly cools over the next 4 hours, the water content cleanly evaporates through the crankcase ventilation system, leaving behind the concentrated minerals and carbon to settle tightly into the microscopic pores of the iron, ready to lock into a permanent tribofilm the next time the engine is brought up to temperature. The pitfalls of haste understand this. This process is unforgiving to those who shortcut the details. There are 3 critical mistakes that beginners make, and each one will neutralize the benefits or cause unnecessary problems. First, never use tap water. Municipal water is loaded with chlorine, fluorides, and heavy dissolved iron. If you heat tap water with borax, those chemicals will react to form a hard, abrasive scale that acts like liquid sandpaper inside your oil lines, tearing up your soft copper bearings instead of protecting them. Stick strictly to natural spring water, sourced from limestone aquifers. Second, do not bypass the thermal dissolution stage. If you attempt to mix the borax into cold water, or if you try to put the dry powder straight into your motor oil, the crystals will never dissolve. They will remain large, jagged solids. The moment they hit your oiling system, your oil filter will recognize them as debris, trap them within the paper pleats, and clog the filter completely within 50 miles. The solution must be perfectly smooth before it enters the engine. Finally, do not drive the vehicle immediately after the treatment. If you put the mixture in and immediately head down the highway under heavy load, the high pressure and shear forces inside the cylinders will sweep the unbonded molecules away before they have a chance to settle and align with the metal structure. You will simply wash the treatment straight into the oil pan, where it will sit inertly. Take your time. Follow the steps exactly as the old practitioners laid them down. On your next regular oil change interval, you will drain the oil, repeat the process with fresh materials, and watch as the machine begins to quiet down, holding its tolerances for the long haul. The molecular architecture let us step away from the physical assembly on the workbench and look directly into the dark, invisible spaces inside the engine block. To truly trust a traditional method, you must understand the unseen forces that allow it to work. It is not enough to simply say that it preserves the iron. We must examine the physical chemistry that modern industrial paradigms chose to overlook. When your engine is running under normal conditions, the fluid film of standard motor oil acts as a hydraulic cushion between moving parts. But under extreme loads, such as the exact millisecond the piston reaches the very top of its stroke and reverses direction, the pressure on the cylinder wall can spike drastically. In that brief moment, the liquid oil is subjected to immense physical force. It behaves like water trapped between 2 heavy blocks of concrete, It simply squeezes out entirely. This leaves the microscopic peaks of the metal surfaces, what materials engineers call asperities, to collide directly with one another. This is boundary lubrication failure, and it is the exact point where microscopic tearing occurs, slowly wearing down the engine over millions of cycles. When our mixture enters this high-pressure environment, the intense friction-induced heat acts as a catalyst for a process known as tribochemical deposition. The borate ions within the dissolved solution possess a natural, powerful chemical affinity for iron oxide. Under the intense localized heat of the metal-on-metal collision, these ions do not simply wash away. Instead, they react directly with the surface molecules of the iron, reorganizing them into an amorphous, glassy layer of iron borate. This layer is extraordinarily thin, measured in nanometers, but its structural properties are completely different from the raw metal beneath it. It is highly elastic under light operational loads, but it becomes exceptionally hard under sudden, heavy impacts. The playing card analogy to understand how the graphite interacts with this glassy layer. Think of the carbon particles as billions of microscopic decks of playing cards floating through the oil lines. When a heavy mechanical load presses down on a deck of cards, the deck does not crush or shatter vertically. Instead, the individual cards easily slide horizontally off the top of one another with almost zero structural resistance. This characteristic is known as planar cleavage. The graphite provides this smooth, low-resistance sliding action across the cylinder wall, while the borax serves as the molecular cement that anchors the bottom card firmly to the iron surface so it cannot be swept away by the scraping motion of the piston rings. At the same time, the dissolved calcium and magnesium from the limestone spring water act as stabilizing agents within the matrix, cross-linking the borate chains and making the entire glassy layer far more resilient against the acidic byproducts that naturally accumulate in crankcase oil from combustion. The hard boundaries of reality now, look at me. Understand this clearly. This is the point where we must separate the romanticism of old workshop stories from hard, objective physical reality. Every traditional method has its strict boundaries, and attempting to apply this knowledge without respecting those limits will result in the destruction of the very machine you are trying to protect. First, consider the metallurgy of your vehicle. This entire chemical reaction relies completely on the presence of iron oxide at the interface. The borate ions require a ferrous substrate to form their molecular bond. If you drive a modern vehicle equipped with an all-aluminum engine block that utilizes an aluminum-silicon alloy like Alusil, or a nickel-silicon carbide coating like Nikasil on the cylinder bores instead of traditional iron sleeves, this method will completely fail. The boron cannot form its protective glass matrix on a non-ferrous surface. The graphite will still offer some minor mechanical lubrication, but the permanent, self-healing shield will never establish itself. The ingredients will simply circulate as loose, unbonded material, eventually ending up trapped in your oil filter. Second, look closely at the mechanical design and tolerances of the machine. The old stationary generators in Holmes County and the domestic trucks built before the mid-2000s were engineered with relatively loose mechanical clearances. They were built to operate on high-viscosity oils like 10W30 or 15W40, pushed by heavy-duty, gear-driven displacement oil pumps through wide oil galleries. Modern engines built within the last 5 to 10 years are entirely different machines. To meet strict government fuel economy mandates, they are engineered with hyper-tight tolerances and utilize ultra-thin oils like 0W16 or 0WD8, which flow with the consistency of water. Furthermore, these modern engines rely on complex variable valve timing systems that direct oil through intricate control solenoids and cam phasers. These oil pathways are often no wider than a sewing needle and are protected by microscopic mesh screens. If you introduce a physical suspension containing solid carbon graphite particles into a modern engine with these hyper-tight parameters, you run a severe risk of plugging those tiny mesh screens. This will starve the upper valve train of oil, trigger immediate diagnostic trouble codes, and cause significant mechanical timing issues. Third, we must look at the emissions equipment. If you are treating an older mechanical diesel, a classic tractor, or a high-mileage truck with traditional cast iron architecture, the system works beautifully. However, if your vehicle is equipped with a modern diesel particulate filter or an advanced sensitive catalytic converter, and that engine is actively burning oil due to worn valve stem seals, you must exercise caution. When an engine consumes oil treated with this mixture, the non-combustible mineral ash, specifically the calcium and the boron solids, will be carried directly into the exhaust stream. Over time, these fine mineral deposits can coat the delicate ceramic honeycomb inside your catalytic converter or plug the micropores of your particulate filter, creating excessive exhaust back pressure and causing premature failure of the emissions system. Stop and think about why the traditional communities can use this technique for over 6 decades without experiencing these failures. It is because they match the traditional solution to the traditional architecture. They apply it to heavy, cast iron diesel blocks, basic utility motors, and older mechanical trucks. They do not pour it into complex, computer-controlled, turbocharged gasoline direct injection engines that require specialized synthetic fluids to protect delicate overhead cam arrangements. If you own a machine built with iron sleeves, a solid cast block, and conventional oil pathways, this method provides a verified, resilient shield against the boundary wear that modern consumer economics accepts as a natural end of life. But if you are driving a modern, high-tech, tight-tolerance vehicle, leave this method on the shelf. Respect the machine you have, and recognize exactly where the old knowledge fits and where the new engineering demands a different path. The paper trail of preservation. Look at the document on the bench before you. This is not folklore, and it is not a modern internet theory. It is a printed copy of United States Patent number 1987-904, officially stamped by the United States Patent Office on August 14, 1933. The man who signed his name to the original application was an independent industrial chemist named Alan Ray Putnam. If you read through the dense, formal text of Putnam's original filing, you will find a highly detailed description of how alkaline earth metal borates behave when suspended in basic hydrocarbon lubricants under heavy load. Putnam wasn't trying to build a corporate empire. He was trying to solve a specific problem for the independent truck drivers and industrial mill operators of the Great Depression era. Men who could not afford to replace machinery every 2 or 3 years. For a brief period in the mid-1930s, his formula was manufactured by a small independent refinery in western Pennsylvania and distributed to service stations across the Midwest in plain metal cans for 25 cents apiece by 1937. That small refinery was absorbed by a larger regional holding company tied to the legacy of the old Standard Oil Trust. Within 31 months of that acquisition, the product was quietly withdrawn from commercial shelves. The patent was moved to a corporate archive. The advertising campaigns ceased. And when Putnam passed away in 1941, the commercial memory of his discovery effectively died with him. But a public patent is a permanent legal record. It cannot be erased. It can only be forgotten. The academic convergence 30 years after Putnam's formula disappeared from American service stations. The exact same chemical phenomenon was rediscovered thousands of miles away, completely independent of the American patent records. In 1964, the Soviet Academy of Sciences was tasked with resolving a severe logistical crisis involving heavy-tracked armored vehicles operating in the extreme sub-zero environments of the Ural Mountains and northern Siberia. Standard petroleum lubricants were thickening or shearing completely under the immense loads, leading to catastrophic engine seizures during prolonged maneuvers. The Soviet researchers began experimenting with inorganic boron polymer additives suspended directly in heavy mineral oils. Their published technical bulletins from the winter of 1964 documented a massive breakthrough by introducing microfine borate compounds into the lubrication system. They observed that the operating lifespan of heavy diesel engines extended from an average of 800 operational hours to over 12,000 hours without requiring a single internal teardown. The cylinder liners showed zero measurable mechanical wear because the metal was completely insulated by the self-healing inorganic film. The Western scientific community finally caught up with these findings in the early 1980s. In February of 1984, a formal paper was published in Lubrication Engineering, the official journal of the Society of Tribologists and Lubrication Engineers. The study, directed by Dr. Marcus Wenzel at the Southwest Research Institute in San Antonio, Texas, evaluated 17 different commercial and chemical additives using high-load Caterpillar 3406 test engines. Dr. Wenzel's lab notebooks, which are preserved in a simple cardboard binder in my office, indicate that the basic borate suspension outperformed every single zinc, phosphorus, and sulfur-based additive on the commercial market. The report noted that the crystalline boundary film did not wash away during routine oil changes, remaining fully bonded to the iron substrate. Yet, within 2 years of the study's publication, the independent freight company that funded the research was bought out by a larger national carrier. The testing program was terminated, and the findings were relegated to obscure engineering libraries. The unbroken chain understand this. While industrial syndicates were buying up patents and academic journals were being filed away in basement archives. The practical application of this chemistry never actually stopped. It simply moved into the quiet spaces of the American landscape. When the commercial barrels of Putnam's original additive mix ran dry in the early 1950s, a blacksmith and elder named Jonas Byler in Lancaster County, Pennsylvania, refused to return to conventional oils. He knew the engine's run on the old compound lasted 3 times longer than those that weren't. Byler pulled the original ingredient lists from old agricultural circulars and realized that common commercial laundry borax shared the exact same chemical foundation as the high-priced industrial additive. He began experimenting with thermal suspensions using a simple coal-fired forge to warm his carrier oils. By the early 1960s, the practice had spread to the old order communities of Holmes County, Ohio. It was there that Eli Miller, Marlin Hostetler's uncle, made the accidental discovery regarding the local water supply. In the winter of 1961, Miller was preparing a batch of the borax suspension for his sawmill's stationary power unit. Finding his rainwater cistern frozen solid, he dipped his bucket directly into the limestone spring house behind his barn. The natural calcium carbonate and magnesium silicate dissolved in that hard spring water didn't ruin the mixture. Instead, it acted as a chemical stabilizer. It caused the borax to form a far more aggressive, resilient bond with the iron cylinder walls. That specific 1958 Wisconsin engine ran continuously at that sawmill until Eli's passing in 2007. And it continues to turn the main drive belt today under the care of his grandson. Reclaiming the bench, look back at the vehicle sitting in your own driveway. It is very likely that you have been operating under the assumption that its lifespan is strictly limited by the numbers on the odometer. You have been trained to accept that a machine must eventually become a piece of disposable consumer waste, forcing you back into a system of endless payments and retail dependency. But the old knowledge reminds us that a tool is not a disposable commodity. A tool is a long-term companion meant to serve a man, his family, and the generation that follows them. This coming Saturday morning, you have a choice to make. You can continue to participate in the conventional cycle of planned obsolescence, or you can walk into a local grocery store, spend less than $4 on a basic box of laundry borax, pick up a $4 tube of powdered graphite at the hardware store, and take control of the physical chemistry inside your own engine block. The method is simple. The materials are completely accessible, and the science has been verified for nearly a century by independent researchers across the globe. You do not need a degree in materials engineering, and you do not need to pay a diagnostic technician $80 an hour to protect your property. You simply need a clean saucepan, a steady hand, and 20 minutes of focused, disciplined effort. Step up to your own workbench this weekend. Follow the steps exactly as they were preserved by the men who've refused to let their self-reliance be bought out or shelved. Give your machine the protective shield it was engineered to hold, and take back the practical independence that was quietly taken from us. I will see you in the shop.